Alright, let's get into section 11.6, talking about absolute convergence and the ratio and root tests. So, given any series, we can consider the corresponding series of the absolute value of a sub n rather than just a sub n, and this is just the absolute value of all the terms in the original series. So, a series is called absolutely convergent if the series of absolute values is convergent. Okay, so we say that a series is absolutely convergent if the series of the absolute values is convergent. Okay? So consider this series, so negative 1 to the n minus 1 over n squared. So this is an alternating series, right, with the primary series being 1 over n squared. So if we look at the series, the sum, and going from 1 to infinity of the absolute value of negative 1 to the n minus 1 over n squared. Okay. This, no matter what the negative 1 power is, so if it's positive 1 or negative 1, the absolute value makes it positive every time. So this is just going to be the series 1 over n squared, right, which is 1 plus 1 over 2 squared plus 1 over 3 squared, etc. And this is a series that we know, right? We've worked with this one before, and even if we hadn't, we could determine it's convergent. So this is convergent. So it's a convergent p-series. Right? Because it's got a p-value of 2. Okay, so that is a convergent p-series. So, thus, the series is absolutely convergent. Alright, so since the absolute value series was convergent, that means the original series is absolutely convergent. Alright, now consider the alternating harmonic series. Okay. So if we look at this sum, and going from 1 to infinity of the absolute value of this one, well that, once you get rid of the negative values, this just becomes 1 over n, right, which is 1 plus a half plus a third, etc., which is just the harmonic series, right? So this is just the harmonic series. And thus divergent. Okay, but we looked in the previous section at this same series, right, the alternating harmonic series, and found that it was convergent. So what does this tell us? Well, this just tells us, so this series is convergent, but not absolutely convergent. And that is possible. It is possible for a series to be convergent but not absolutely convergent, as we see here. Okay, and this type of series actually has a special name. So a series that is convergent but not absolutely convergent is called conditionally convergent. Okay, so for example, the alternating harmonic series is considered conditionally convergent. Okay. Now, why do we care about whether a series is absolutely convergent or not? Well, because of this theorem. This is a very good theorem for us. If a series is absolutely convergent, then it is convergent. Okay, so sometimes we're not able to work with a series as easily to determine convergence, but maybe by taking an absolute value, we can work with it better. So in that case, we can show that it's absolutely convergent, and if it's absolutely convergent, then it is convergent. Okay, so now we're actually going to prove this theorem, so it's a nice kind of concise proof here. So observe that 0, oops, let me zoom in here, 0 is less than or equal to the series plus the absolute value of the series, which is less than or equal to 2 times the absolute value of the series. Okay, so think about that for a second. So we have that if we take the series plus its absolute value, that's going to be greater than or equal to 0, but less than or equal to 2 times the absolute value. And this is because the absolute value of the series is either just the series itself or the opposite of the series. Right? So if the series had a negative value, the absolute value is positive, in which case then they balance out to 0. But if the series was positive, the absolute value just keeps it positive, so their sum would just be double. Okay, so those are the two boundaries there on those outcomes. Okay, then we can say if the sum of the series a sub n is absolutely convergent, so if it's absolutely convergent, then that means the sum of the absolute values is convergent. Right? That's what it means to be absolutely convergent. So, if the absolute value of the series is convergent, then certainly 2 times the absolute value would be convergent. Right? If it converges to a finite number, well, if you double it, it's still going to converge just to whatever double that number is. Okay? So this is also convergent. Okay. So we can then say, thus, by the comparison test, what's going on with this? There we go. So thus, by the comparison test, right, because with the comparison test we compare a known series with our unknown series. So the sum of a sub n plus the absolute value is convergent. Right? So again, we just showed that because we're assuming that the series is absolutely convergent, that means its absolute value is convergent. So that means double its absolute value is convergent. And since that double absolute value is greater than or equal to this, and it's convergent, by the comparison test, something smaller than it must also be convergent. Okay, so that gives us that sum is convergent. Then, this gives us the series a sub n, which is equal to the sum of a sub n plus its absolute value minus the sum of the absolute value. Okay, so we know that this series is just the combination of this minus this, right? Because I'm just adding the absolute value and then taking it away, essentially. So those two are equivalent, they're equal to each other. So, but since we just showed that this series is convergent, and we showed that this one is convergent, well then this one, because it's the difference of those two, must also be convergent, right? Because it's a finite number minus a finite number, that has to also be a finite number. So then this series is the difference between two convergent series, and is thus convergent. Okay. So, and then, of course, that's the end of our proof. So just signify that. Okay, so let's just run through this really quickly one more time all together here. So observe that because the absolute value is either the same as the series or its exact opposite, that means that the sum of the two must be greater than or equal to 0 and less than or equal to double what the absolute value is, right? The positive one. If the series is absolutely convergent, that means that the absolute value is convergent by definition. And that tells us that certainly double the absolute value must also be convergent. And we know that that double of the absolute value is bigger than this sum. And if the bigger one is convergent, the smaller one must also be convergent. Okay, so therefore we get that that sum is convergent, and our original series A can just be written as a difference between the sum with the absolute value minus the sum of the absolute value, right? Take away the absolute value. And because it's a difference of two convergent series, then it must also be a convergent series. And there we have it. So a nice clean argument there to prove this theorem. So, and now this theorem can be very useful to us. So let's look at an example. So determine whether the series of cosine of n over n squared is convergent or divergent. Okay, so first thing I want to make a note about here is, now this series does have some positive and negative values. Positive and negative values. But it's not alternating. Okay, and that's going to be an important feature of this. Okay, it is not an alternating series because even though some values are positive, some are negative, it doesn't have any specific order to it. It's not going like, negative to positive to negative to positive like that. So it does have positives and negatives, but it's not alternating. So we couldn't perform the alternating series test here even if we wanted to. So let's use the comparison test. Alright, so here we have the sum n going from 1 to infinity of the absolute value of cosine of n over n squared. N squared is always positive, so we can just keep the absolute value on the cosine. We don't need it on the n squared. So absolute value of cosine of n over n squared. Okay, so let's think about what we know for the cosine function. So we know the absolute value of cosine of n must be less than or equal to 1. Okay, right, that's just a property of cosine, right, that trig function. So cosine is always between -1 and 1, and then since its absolute value, it must be just less than or equal to 1. And that is for all n. Okay. So there we go. So, what that gives us is that the absolute value of cosine of n over n squared, since absolute value of cosine of n is less than or equal to 1, this fraction must be less than or equal to 1 over n squared. Okay, and we know 1 over n squared is convergent. So, the sum of the absolute value of cosine of n over n squared is also convergent by the comparison test. Okay. And now since this one is convergent, that's the absolute value of that series is convergent, we can say thus our original series, cosine of n over n squared, is absolutely convergent. And if it's absolutely convergent by our theorem up above, that means it's convergent. So, and therefore, convergent. All right. So we have that our series here must be convergent using a combination of the comparison test with this property of absolute convergence that we just talked about. Okay, so let's move on to a couple of new tests that we're going to be able to use. So the first up is the ratio test. So the ratio test says we're looking at the limit as n approaches infinity of a sub n plus 1 over a sub n. Okay, so if the limit of the absolute value of that quotient, which is L, if that limit is less than 1, then the series is absolutely convergent. Okay, and thus convergent. And if that limit value is greater than 1, or it heads towards infinity, then the series is divergent. Okay, and if the limit equals 1, then the ratio test is inconclusive. Okay, so that is, no conclusion can be drawn about the convergence or divergence. So if we have the limit is less than 1, it's absolutely convergent, so convergent. And if the limit is greater than 1, it's divergent. And if the limit equals 1, then the test doesn't really tell us anything. Okay, so let's use this to try a couple examples. So first up, we have the series -1 to the n times n cubed over 3 to the n. So we're going to use the ratio test. with the series negative 1 to the n times n cubed over 3 to the n. Alright, so let's set up the absolute value of the ratio. So a sub n plus 1 over a sub n. So this is going to be, so you're going to need some space here for this fraction. That's going to be negative 1 to the n plus 1 times n plus 1 cubed over 3 to the n plus 1 over negative 1 to the n times n cubed over 3 to the n. Okay. And then this, if we go ahead and write this out, we're going to get n plus 1 cubed over 3 to the n plus 1, right? That's from our numerator. Denominator multiplied by its reciprocal. We're going to get 3 to the n over n cubed. Right? And then regardless whether this was positive or negative, one of them was going to be negative while the other was positive, and we took the absolute value. So it just made everything positive, so we can get rid of those. Okay, and then here we have, so 3 to the n plus 1, so that's n plus 1 copies of 3. This one has n copies of 3, so this one has one more copy of 3 than this one does. Okay, so when we cancel these, we're going to cancel all but one of the 3's in the denominator. And the ones in the numerator are all just going to go away because they get canceled out. So this is going to become 1/3 times, notice the n plus 1 and the n both are raised to the third power. So we can go ahead and just turn those into one term, like this. Okay, so a little bit of simplification there. And then this, if we expand this out over that common denominator, this becomes 1/3 times 1 plus 1 over n cubed, which as n goes towards infinity, right, the limit as n goes towards infinity, that heads towards 0. So that means we have 1/3 times 1. So that approaches 1/3, which is less than 1 as n goes towards infinity. So our ratio that we got, okay, we took the limit of that ratio and got 1/3, which is a value less than 1. So, thus, by the ratio test, the series is absolutely convergent. So we got that it is absolutely convergent. Alright, let's look at another one. So test the convergence of this series. So n to the n over n factorial. So really interesting functions here. So first off, let's notice something that's going to make our work a little bit easier. So notice that our series n to the n over n factorial, n is going from 1 to infinity, so n is always positive, so this series is positive for all n. Whoops. For all n. And since it's positive for all n, when we do the ratio, we don't need the absolute value. So we don't need absolute value. So just a little something to help simplify our work a bit. So we're going to get a sub n plus 1 over a sub n. So that's going to be n plus 1 to the n plus 1 over n plus 1 factorial over n to the n, n to the n over n factorial. Let's go ahead and write that as multiplication by the reciprocal. Okay. So now, let's go ahead and play around with this algebraically. So again, remember n plus 1 factorial is the same thing as n plus 1 times n factorial. Okay, and then n plus 1 to the n plus 1 power up here, that's the same thing as n plus 1 times n plus 1 to the n. Right, I basically just took out one of those factors of n plus 1, and down here we have n plus 1 times n factorial, and that's times n factorial over n to the n. So now we can do some cancellation. So we get that cancels with that cancels with that. These two have the same power on them, so we can combine them into one term. So that's going to be n plus 1 over n to the n, which is 1 plus 1 over n to the n. This might look vaguely familiar to you, depending on how in-depth you went into it in Calc 1. I know when I teach Calc 1 I mention this, but this is actually a special relationship that we have. This is a special term. This is actually, if you take the limit as n approaches infinity, this value approaches e. So this is actually the limiting function for e, right? The natural exponential number. So that approaches e as n approaches infinity. Okay, so then we can go ahead and make our conclusion, because we know that e is approximately, right, 2.7 yada yada yada. So since e is greater than 1, the series is divergent by the ratio test. And there we have it. Okay, so we play around with these expressions, and we got down to a form that we hopefully can recognize, at least hopefully now we can, and then we were able to run our test with it. Okay, so let's look at the next page here. We have one more test to talk about today, and that is the root test. So the root test is actually very similarly related to the ratio test, but it's dealing specifically with, of course, roots, right, with fractional powers here. And so these come in handy a lot when you have a lot of high powers in your series, in your expression. So if we have the limit as n approaches infinity of the nth root of the absolute value of a sub n, if that is less than 1, then the series is absolutely convergent. If that limit is greater than 1, then the series is divergent. And if the series, if the limit equals 1, then the root test is inconclusive. And then I do need to make a note here for everybody. So if you run this test and you get that it's inconclusive and you think, well, maybe I'll go try the ratio tests. You don't need to. So the root and ratio tests actually will be inconclusive at the same time. And that's something that we could prove, but of course we're not going to take the time to do that. But just so you know that if you try one of these tests and it gives you an inconclusive result, don't bother trying the other one, because it's a guarantee it will also be inconclusive. Okay, so we don't need to waste our time running more tests that aren't even going to work for us. Okay? So let's look at this example down here. So test the convergence of the series of 2n plus 3 over 3n plus 2, all raised to the n power. So our series, right, this is 2n plus 3 over 3n plus 2 to the n. So let's get this nth root of the absolute value so that we can run this root test. So we have here the nth root of the absolute value of that series. So now the absolute value isn't going to change anything, so that's just going to be 2n plus 3 over 3n plus 2, because n is always positive. And then when we take the nth root of the nth power, they're inverse operators on each other. They undo each other, or you can think of it as they cancel each other out. So that's all we're going to have left is just 2n plus 3 over 3n plus 2, and that's precisely why we like using the root test on high powers, because it gets rid of the power. And now we can just play around with this as we normally would play around with limits, so that becomes 2 plus 3 over n over 3 plus 2 over n. As n goes towards infinity, that goes to 0, that goes to 0, so the whole thing goes to 2/3, which is less than 1. So since it goes to a value that is less than 1, we can say thus, the series is absolutely convergent by the root test. Thus, since it's absolutely convergent, it is convergent. And there we have it. All right, so that brings us to the end of section 11.6 and the end of the lectures for today. So when we come back next time, we're looking at more types of series, more tests, all that good stuff. So we're getting closer to the end of chapter 11 here. Keep up the good work, guys, and I will talk with you all next time.